Hey everyone, we're here for our next little bit of the AP Calculus final review. This video will start with question 11. So we'll get going here right now. So we're supposed to evaluate this integral. We've got a cosine t on the numerator, and on the denominator we have ourselves a 2 minus sine t to the fourth power. And when I look at this, I immediately think that the derivative here of 2 minus sine t, well, that's going to be negative cosine t. The negative doesn't bother me because it is constant. The cosine is actually the numerator, so that leads me to believe that I can get this integral done just by using a regular u substitution. So I'm going to allow u to be equal to sine 2 minus sine t. You don't have to worry about the exponent here. As you gain some experience, you'll see that these exponents, they're actually going to work themselves out and be included in a power rule. Now, if I take the derivative, I get that du is equal to negative cosine dt. And if I move that negative over, I get that cosine t dt is equal to negative du. Now with the original integral, I'm going to go ahead and re-express this a little bit. We've got 1 over the quantity of 2 minus sine t to the fourth multiplied by the quantity of cosine t dt. Now this cosine t dt, that's the same thing as negative du, so we'll make that replacement. And then down on the denominator, we're going to go ahead and turn this 1 over sine 2 minus sine t to the fourth. We'll make that replacement with u. And then we'll use a negative exponent to get u to the negative fourth power. Simplified, we get the negative integral of u to the negative fourth du, which we can use a simple power rule on. Now you'll need to be a little bit careful here because negative 4 plus 1 is negative 3. So if you don't have your integer addition thinking straight, then you might make a problem here, or make a mistake here. We'll get rid of the negatives because we have 2 of them. And then we'll substitute. No, let's not substitute. Let's do that u to the negative 3 power. We'll simplify that. And then we'll substitute back for our u. Our u was 2 minus sine t. And then just a little cosmetic thing. We don't need the parentheses. And we can carry through the multiplication to the denominator. And that completes our problem, number 11. Let's take a look at 12 now. We've got another integral. This one's a little bit easier. The 2 terms here are separated, so we can just do each one, integrate each term separately. We could probably turn that 1 over x to the fourth, we'll turn that to x to the negative 4. And now we're ready to apply our power rule. Taking a look at each of the exponents, 6 plus 1 is 7. Negative 4 plus 1 is negative 3. We have a plus 1 over negative 3. We can simplify the negative sign. And then we can simplify that x to the negative 3 power. And then multiply those fractions through. And that does it for number 12. Moving on to 13, we have a general power rule to evaluate the integral. Now, this one says use general power rule. But when I look at the integrand, I notice that inside the square root, I've got a 4 minus 9x squared. And if I take the derivative of 4 minus 9x squared, I get myself a negative 18x. And there's an x here. Again, that negative 18, that constant multiple does not bother me at all. I can use that in any substitution method. So I believe we're going to use the substitution method. So let's make our u. As we discussed, that u is going to be 4 minus 9x squared. Now we'll take some derivatives. And then we'll divide both sides by 18. Should have said negative 18. Simplify. Great, and we've got x dx is going to equal negative du over 18. Let's get to our original problem. So maybe our first thing to do is to do a little bit of regrouping. Then we could do some substitution. And then we'll substitute for that x dx also. We'll take this opportunity to do a little bit of simplifying. That negative sign can work its way to the front of the integral. And that du over 18, well, we can turn that into 1 over 18. And that move that 1/18 to the front. And then u square root of u, we can turn that to u to the 1/2. And now that we have this all simplified, we'll apply a power rule. U to the power 1/2, 1/2 plus 1 is going to be 3/2 power. So our new power will be 3/2, and we're going to have to divide by, or we're going to multiply that by 1 over 3/2. All right, that's a lot to take in. That this 1 over 3/2 right here, we'll just turn that to 2/3. We'll multiply those fractions. Simplify that u, or let's substitute that u back in there. U was 4 minus 9x squared. And then we'll simplify out that negative 1 over 27. And I think that does it for number 13. Great. That's great. Let's take a look at our next problem, number 14. We've got another evaluate the integral. I'm looking at this again, and I am noticing that the derivative of x squared plus 1, which is the integrand, is going to be equal to 2x. The 2 doesn't matter, but the x does, because I have an x outside of the square root to balance that out. So that's going to be my approach. If you see me do these in class, you know that I like to find the antiderivative first. So we'll find the antiderivative before we deal with a definite integral. So if we start with the premise that u is equal to x squared plus 1, we get to du is equal to 2x dx, which is equivalent to du equals x dx, sorry, du over 2 equals x dx. And that makes us ready for our substitution. Let's write down our integral again. Now we're going to rearrange things to get ready for our substitution. I'm going to get those x and the dx together to start off with. And then we'll substitute that x squared plus 1. And then we'll substitute that x dx. And then we'll simplify that du over 2 into 1/2 du. We'll move that 1/2 to the front of the integral. Then we can change that u square root of u into into u to the 1/2 power. And that makes us ready to use our antiderivative rule. So let's write down our pieces. We'll first take that u to the 1/2 and we'll add a 1 to it. Then we'll divide by our new power, and then plus c. 1 over 3/2 power, that's the same thing as 2/3. Then we can multiply 2/3 and 3. 2/3 and 1/2, I mean. Great, and this is our antiderivative in terms of u. We'll substitute our x's back into here, because we know that u is the same thing as x squared plus 1. And that does it for our antiderivative. Now we're ready to use the fundamental theorem of calculus to evaluate the definite integral. So this is going to be the antiderivative evaluated at 1 minus the antiderivative evaluated at 0. Okay, let's do some simplification. First, we'll deal with those powers. Whoops. Then we'll do some addition. Now 2 to the 3/2 power, I don't have a number for that, but I can simplify that or make it cosmetically nicer. Actually, I just looked at the answer key and I don't need to do that. 1 to the 3/2 power, that's just equal to 1, which I don't even need because 1/3 times 1 is just 1. And then I suppose I could factor out that 1/3. And that just about does it with question 14. Let's just summarize this at the end here. That'll just about do it for question 14. Let's look at 15. Now 15 is another one of those classic substitutions. This time I have inside the cosine x over 4. So it looks like this is going to be a pretty easy one. Let's go ahead and set up our u substitution. If we make our u equal to x over 4, our d is going to be 1/4 dx. Looking at my integrand over here, I don't see any place to balance out that 1/4. So I'm going to go ahead and pop that to the other side. Great. Now we can start working on our integral. So my first substitution, instead of x over 4, I'm going to make that a u. And then this dx, we're going to replace with x over 4 du. Perfect. Now we can take that 4 and move it outside of the integral. Awesome. Now we just have a nice clean integral. The antiderivative of cosine u is sine u plus our constant. And then lastly, we can substitute u back. U is x over 4. And that just about does that with number 15. 16's turn. Okay, look at this one. This is interesting. Now, for this one, I think the best thing to do is to, well, let's see. Can we do this with a regular integral? And of course, the answer is no. What about for a u substitution? Well, slim pickings here because the inside the sine function is just an x. And of course, substituting u equals x squared isn't really going to do anything. So I think we're kind of down to our last little technique here, which would be an integral by parts. Now, a lot of us are doing tabular method, so I'll go ahead and respect that. And we'll do some tabular method. Let's take a look at u dv. Just going to put a couple of lines here because I don't know how many we're actually going to need. Now, using the table just kind of presumes that you already know how to use the integral by parts, or the ultraviolet voodoo. On the left side, we're going to keep taking derivatives. The derivative of x squared is 2x. On the right side, we're going to take antiderivatives. So the antiderivative of sine is negative cosine of x. And then we should probably put our third line here, our third column. And of course, I'll ask myself if I can take the antiderivative of 2x cosine x, and the answer is no. That's how I know I need to keep going on with this chart. The derivative of 2x is 2. The antiderivative of negative cosine x is negative sine of x. We multiply that together, we get a negative 2 sine x, and we can ask ourselves, can I take the antiderivative of that? The answer to that question is a yes. However, I notice that I have a constant here, and if I go to the derivative one more time, then that'll save me a whole lot of trouble. So I'll do one more line of this table so I can get that 0 in the bottom right-hand corner. The derivative of 2 is 0. The antiderivative of negative sine x is cosine x. And when I multiply those two together, I get a 0, which is a highly coveted number, because that's going to mean that I can stop here. So let's go ahead and assemble our antiderivative. The first thing we're going to do is multiply diagonally. This is going to be x squared multiplied by negative cosine x. From that, we're going to subtract 2x multiplied by sine x, negative sine x. And to that, we're going to add 2 times cosine x. And then we're going to add a constant at the end there. Now we can set about simplifying things. I actually should mention that at the bottom here, this last column, we got a 0. So we actually don't have to do any further integration. That's the reason why we like to get those zeros. Now that we've done that, let's do some simplifying. Okay, we can take this negative right here and we can move that on the outside. We got x squared cosine x, and there's nothing more to simplify there. Okay, next term we have minus here, and then another minus here, so that'll make a plus. And then the 2x multiplied sine x, there's not a whole lot to do there. And then finally over here we've got 2 and cosine x. Again, there's not much to simplify there. And that really completes our answer for this one. Not much else to do, and we're ready to move on. Great. All right, so this is going to be another one of those antiderivatives by parts. And just like last time, this is an opportunity for us to use a tabular method. So let's use a tabular integration by parts. Again, I don't know how many lines I should use, so I just put a few here. Taking a look at the integrand, I have an algebraic piece, that's that x squared. I also have an exponential, e to the 3x. And if I go down the list, L-I-A-T-E, I have algebra A before exponential E. So I'm going to make x squared be my u, and I'm going to make e to the 3x. I'm going to make that be my dv. All right. All right, we're ready for our first step, would be to the derivative. Do the derivative. The derivative of x squared is 2x. Now be careful here because we need the antiderivative. And the antiderivative of e to the 3x, well, that's 1/3 e to the 3x. Let's multiply that out together. That's going to give me 2/3 x e to the 3x, which does not look like I can find an antiderivative, so we'll run through the entire program again. The derivative of 2x is 2. The antiderivative of 1/3 e to the 3x, well, that's 1/9 e to the 3x, and when I multiply everything together, I get 2/3 e to the 3x, which means I could stop here technically, or I could stop here, period, and I would be able to find the antiderivative. But I note that there's a 2 here in my u column, and if I take the derivative of 2, I'm going to get a 0, which is the best situation of all. So let's do this one more time. The derivative of 2 is 0. The antiderivative of 1/9 e to the 3x is 1/27 e to the 3x. And now when I multiply together, I get myself a 0, which I absolutely love. And we are ready to assemble an antiderivative. Let's put it right over here. First, we multiply x squared times 1/3 e to the 3x. And then we subtract 2x multiplied by 1/9 e to the 3x. And then we add 2 multiplied by 1/27 e to the 3x. And then now I'm at the situation where the next line is 0. So I'm just going to stop here and add my constant. Okay, now we can set about simplifying this entire thing. So I'm going to start by multiplying all of these together. That's a good first step. The next thing I'm going to do is just to factor out all the e to the 3x's. And then I'm going to take these denominators here, and I notice I have a 3, 9, and 27. And the least common multiple is 27. So I'm going to try and get all of these to look like a 27. So this 1/3 over here, that's the same thing as 9 over 27. 2 over 9, well, that's the same as 6 over 27. And then now when I let's just simplify that further. Simplify is kind of weird, but 9 over 27, that's the same as 9 times 1/27, which we can just put in front of the x squared. We'll do the same thing with 6 over 27. We'll make that 6x multiplied by 1 over 27. And then 2 over 27, we can make that 2 multiplied by 1 over 27. And now you can see I've set myself up to factor out that 1 over 27. And then we can simplify that e to the 3x multiplied by 1 over 27. And that just about does it for simplification. So that's about all the time we have for this video. We got through question 17, so we did questions 11 through 17. And we'll see you next time here for more of our calculus final review.